In my last video, I built this Stirling engine to power a bike.
Is that running by itself? That's running!
And whilst I was extremely excited to get it running, the performance was very poor. However, like with any engineering project, there are many things to optimise. This video is sponsored by War Thunder. More on them later. The biggest issue I had in the last video was the expansion of the hot air wasn't pushing the piston far enough, which was temporarily solved by using a shorter crank offset. But when I designed this engine, my calculations showed that it should produce sufficient expansion. So where is all the expanding air going? Inside of this bottom cylinder is what's called the displacer piston, which simply pushes air between the hot and cold sides of the engine. And it's essential that the volume inside of this piston is airtight, which it currently isn't. To fix this, I designed a new bottom plate for the displacer and used high temperature epoxy to bond it to the stainless steel cup, which should create an airtight seal. There is still a small hole where it joins to the output shaft, but once bolted together, this hole will be sealed too. I also removed the main power cylinder and purchased a cylinder honing tool, which helps smooth the lines caused by the machining process, as well as creating a fine crosshatch pattern in the cylinder wall for better lubrication when oil is applied. And I machined a new piston that is specifically designed for these TPU 3D printed cup seals that provide an excellent seal with very little friction. And this is clamped to the piston with a Teflon ring that will run along the inside of the cylinder. So with the old larger crank attached to the engine, which didn't work before, will it now run with the new modifications? Not only is it now running with the expected expansion amount, but the larger crank offset means a higher torque output, and it's spinning at a higher RPM too. However, the expansion of the air isn't the only thing that creates power, as we also need to contract the air by cooling it, which is the job of this side of the engine, hence the air cooling fins and the water cooling pipes. However, the water only cools the rear engine block, as it's separated from this section with a small gasket. So when running these stationary tests, the air-cooled section struggles to stay cool. So I removed it from the engine and retro-machined some water cooling channels into the underside of the block, which probably won't cool the whole block evenly, but it should help a bit. Also, as the air cools down, it contracts and creates a vacuum inside of the engine, but these cup seals on the piston only work when pressure is applied on one side, as the cup expands to seal with the cylinder walls. But if there is a vacuum on this side, air will simply flow past the seal. So I've modified the piston to now use two cup seals mounted in opposite directions, which should still create a seal under vacuum. This double acting piston seal also makes the engine far easier to start, as when the air contracts and pulls a vacuum, the piston doesn't have to fight against compression. It's simply pulled and pushed in both directions. And we've gained an extra 100 RPM. Up until now, I've focused on the heating and cooling of the air, though having to heat the air and then dump the excess heat out through the water cooling every cycle is very inefficient. But there is a way to recycle some of this heat energy using a regenerator. Now this sounds far more complex than it actually is, because a regenerator is simply a high surface area thermally conductive material, like a fine steel mesh, that's placed between the hot and cold sides of the engine, and the air is forced to flow through it. So as the hot air flows around the displacer piston, it deposits some of its heat energy into the mesh by heating it up, which also slightly cools the air. Then after it's fully cooled by the cold side, it flows back through the regenerator mesh, which heats it back up, as it reabsorbs some of the heat energy it previously deposited, recycling the heat it would have otherwise lost to the outside air, meaning less energy is required to heat the air and less heat needs to be removed by the cold side. Traditionally, this regenerator material would be stationary inside of the engine cylinder. However, I want to mount it to the outside of the displacer piston, which essentially does the same job. To do this, I cut some thin silicone sheet to wrap around the outside of the displacer piston, which will insulate the regenerator material from the displacer, as well as allowing it to grip the piston and hopefully prevent it sliding off. Then I bought some fine stainless steel mesh, which I can cut to shape and wrap around the silicone sheet, and used copper wire to tie it in position. But can such a basic modification make much of a difference to the engine's performance? Well, let's mount it back in the engine and find out. With the engine now spinning at 588 RPM compared to the previous 326 RPM, I'm amazed at how adding just a small amount of stainless steel mesh can make such a huge improvement to the performance. Though it doesn't quite sound right, at least for a Stirling engine. It almost sounds like a combustion engine, though there's no combustion, at least internally. Once the engine slowed down, I noticed this crank bolt was loose, which probably caused the knocking sound, but also noticed some wobble in this shaft that's linked to the power piston. In part 1 of this project, I used a Teflon bushing here to allow the shaft to run smooth, but it had far too much play, so I upgraded it to a linear bearing. However, that seems to have gained some play too. I ended up ordering a few different brands of high quality expensive bearings and precision shafts. However, they all seem to have some play, and I think it's because they're designed for smooth travel along the shaft with minimal play in this direction. But I need very little rotational play, which you'd usually solve by just using 2 bearings together. But because I don't have the space for that in my current engine design, I need to make my own linear bearing. To do this, I machined a small part that has 4 threaded holes, which I can mount very small ball bearings to. This creates a V-shaped channel that the shaft will hopefully travel smoothly along, and I can mount this to the back plate of the engine with another bearing block that holds 2 more bearings, sandwiching the shaft to a single axis of movement, and the play has essentially been eliminated. Before running another test, I wanted to check the Regenerator material was okay, but after removing the cylinder, it was obvious there was a problem. There was a strange white powder inside the engine, which seemed to be from the silicone sheet, and it was everywhere. However, after removing the mesh, it seemed only the top portion of the silicone had burnt, as it's closest to the hot cap. So my quick and easy fix was to just cut off this burnt section and shorten the Regenerator, but I also doubled up the thickness of the mesh to make up for the lost material. Did you know one of the most famous uses for a Stirling engine was to quietly power a Swedish submarine, making it almost undetectable underwater? And while I can't get a hold of one of those for testing, I can command a battleship, pilot a fighter jet, or drive a tank, thanks to the sponsor of this video, War Thunder. War Thunder is the most comprehensive vehicle combat game ever made. You can take control of over 2,500 vehicles from 10 major nations, spanning everything from early World War II tanks to modern fighter jets and attack helicopters. And what I really like is the level of mechanical detail, like the way the engines sound, and how the control surfaces move on the aircraft. It's perfect if you enjoy understanding how real machines work, and you can play War Thunder for free right now on PC, PlayStation, Xbox or mobile by using my links in the description. And if you're a new player or haven't played in the last 6 months on PC or console, you'll also get a massive bonus pack with premium vehicles and 7 days of premium account time. It's available for a limited time only, so make sure you grab it while you can. Whilst using a blowtorch to run this engine works well, it's rather loud, which spoils the nature of a Stirling engine being so quiet. So I wanted to build a more permanent burner that won't be as loud. My idea is to have a high surface area heatsink out of this copper sheet, as it will conduct heat from a fire into the hot side of the engine. The heatsink uses 5 plates with a bunch of machined holes that allow the heat to pass through, though the holes in each plate are offset so the heat doesn't have a direct path through and is hopefully conducted into the copper as much as possible. It can then be directly bolted to the hot end of the engine, and for an initial test I bought this small methylated spirit burner to see if it will run the engine. After several minutes, the copper started to oxidise and lose its shiny colour, and the engine still wasn't hot enough to run. So I added some fireproof welding blanket to hopefully insulate the engine and allow the temperature to rise higher. But it still wasn't getting hot enough. I then bought some alcohol burner wick to make my own burner, and I ran some tests by heating some water. By measuring the temperature rise of the water, I can calculate the heat energy produced by the flame, which for a single wick was a little over 200 watts on average. So I made a custom burner out of a steel tin and used 4 wicks to hopefully produce 800 watts of heat, and filled the tin with methylated spirits. With the copper heatsink also insulated, the engine temperature was able to rise far higher, though we now have another issue.
Something's burning more than it should.
After extinguishing the flames, I wanted to at least get the engine spinning, so I filled up the burner with some more methylated spirits and continued heating. And with the hot side of the engine at 240 degrees Celsius, the engine started to run. I do find it quite satisfying seeing a flame on one side and motion on the other, produced completely by the heating and cooling of air. But it also feels like a big step backwards in terms of power output. So before I spend any more time trying to make a proper burner for this thing, I think I'm going to go back to the trusty blowtorch, because I know this produces enough heat to run the engine. What I'm thinking is simply mounting it to the front of the bike like this, which would look a bit ridiculous, but it should be fine for just some initial test rides. Then I need to build a clutch system to replace this flywheel so we can drive the rear wheel, and also finish up adding all the water cooling with its own integrated pump and radiator, just to see if this will actually power the bike. Then if it does, I can spend a bit more time trying to optimize it and making this burner work properly. So I removed the burner and cylinder assembly to reveal the not so nice looking copper heatsink. But after removing it from the hot cap, I had a thought. Maybe I should try increasing the internal surface area of the hot side to heat the air more effectively. Unfortunately, this is difficult to machine into the stainless steel cap, but a quick and easy idea I had was to cut some of the same wire mesh used for the Regenerator and mount it inside of this cap using these small tabs. This probably isn't as good as a machined heatsink, but it's an easy modification and worth a try. I then designed a bracket that clamps to the blowtorch handle, as well as clamping to the bike frame, with the perfect angle to hold the torch nozzle right next to the hot cap of the engine, which looks rather ridiculous, but saves me from holding it. The next step is to build the clutch, which requires a new flywheel that I 3D printed and used bolts to increase its weight. Then for the clutch material, I bought this nitrile rubber bonded cork material that should provide a good amount of friction and has an adhesive on one side to bond well to the flywheel. Then for the other clutch plate, I've chosen to use sandpaper as it's cheap and provides excellent grip against the rubber cork, with very little pressure required. Once the sandpaper disc is cut out, I can simply stick it to the clutch plate with double-sided sticky tape. Sure, this clutch probably won't handle a huge amount of power like a real engine clutch, but for the power output of this Stirling engine, it should survive just fine. And the two plates can be pressed together using a small lever that is designed into the clutch mount, which will be pulled by a cable. So once assembled with a small spring in between the plates, the clutch can be mounted to the bike frame, and I can route some tubing up to the handlebars, where a super simple thumb-controlled clutch lever can be mounted. This clutch lever is only 2 parts, and pulls the cable that controls the clutch at the rear of the bike, pressing the 2 plates together and hopefully engaging the drive to the rear wheel. So let's fire up the blowtorch and give it a test. With the clutch engaged, I can spin the wheel to bump start the engine. But watch what happens when I disengage the clutch. It rapidly accelerates to over 800 RPM, and I can re-engage the clutch to bring the RPM down again, whilst accelerating the wheel up to speed. With the blowtorch turned off, it's clear that my linear bearing solution runs far smoother. And the added mesh inside of the hot cap heats the air far quicker, resulting in a much higher RPM when the clutch is disengaged. Now all it needs is its own integrated water cooling system, which I've chosen to go with a PC style radiator as they're cheap and use the same pipe fittings as my engine, which clamps nicely inside this portion of the frame. Then to pump the water, I bought this small 12 volt pump, which doesn't currently fit my pipe fittings, but instead of buying the correct adapters, I decided to remodel the top portion of the pump and print it on my Formlabs Form 4, because this allows me to create a small reservoir above the pump to make filling the system easier, and the pipe fittings can be threaded in without the need for any adapters. Also, once mounted to the bike frame, the pre-designed angles on these fittings are far more suitable for the tubing to run up towards the engine and radiator, and I can use a small funnel and tubing to fill the system with water. Now this pump is rated for 12 volts, but when I increase the voltage to 12 volts, it starts cavitating and becomes really inefficient, and it seems to run best at about 3.5 to 4 volts, which is perfect because I can run the whole system off a single lithium ion cell, and it only draws about 2 watts of power. I think it's time we take this bike for a test ride.
Just waiting for my bike to warm up. Right, whilst it's heating up more, I might just take it for a bit of a ride because I'm worried that the radiator is going to get too hot when it's got no airflow on it. I'll tell you what, it's warming up my legs riding this. It's quite nice actually. It's like having a heated seat. I've never had a heated seat on a bike. Oh, now it's running. I think we need to add some kind of air shield here because it's not quite getting hot enough on the front. Okay, so I've now made a very DIY windbreak so that hopefully it gets hot enough now. And engage the clutch. Oh, I stalled it. It has some power. I can feel it the tiniest bit. It's just not very much. Like, I reckon it's maybe like 30 watts at best. I'll tell you what though, that is running for quite a while.
I then thought it might run better at higher speed, as the extra airflow will help cool the radiator and the cold side of the engine, creating a larger temperature difference, as well as potentially allowing the engine to run at a more optimal RPM. So I pedalled up to speed and engaged the clutch.
It's not pedaling.
Ever seen a Stirling engine powered bike before?
Can't say I have.
Good day, sir.
Good day. What on earth is that?
It definitely runs better at higher speed. I don't know whether it hits a power band, it hits like an optimal efficiency RPM, or the water cooling is just better at higher speed. It's still not quite enough to like maintain a constant speed, but it's close. It's so close.
Right, so now it's Sam's turn on the Stirling bike. It's going to be interesting how Sam finds this bike because he weighs about 20 kilos less than I do, so the tiny boost from the engine might assist him a bit more than it does for me.
And engage power.
So the weight reduction allows the engine to give a very small boost. But how will it run when Sam tries it at higher speed?
Oh, that is so pushing me along. It's so cool how it sounds.
While the engine applies a very small amount of power assist, it's not going to push me up any hills. But I think it's important to remember that with some relatively minor modifications, the engine went from this
It's actually running.
to this. And I think it will spin a lot faster by increasing the heat transfer inside of the engine, which would allow for a better pulley ratio to achieve more torque, and possibly maintain a constant cruise speed. But for now, thank you very much for watching. Oh, and before you go, don't forget to check out War Thunder, which you can download for free on PC, console, or mobile by going to the link in the video description. Thank you once again to War Thunder for sponsoring this project.